Welcome to lecture 17 of solitons. So last time we studied the asymptotics of the two soliton solution that we obtained by a double Backlund transform of the vacuum. And I remind you, these were solutions of the Sine-Gordon equation. And what we did was to go to a comoving frame which moves at constant velocity v, and then take the limit where time goes to plus or minus infinity with fixed comoving coordinates. And we saw that if we took the velocity of the comoving frame to be equal to the velocity of one or the other solitons which are contained in the solution, we could actually follow the trajectory of the two constituent solitons at early times and at late times. So here you see plot of the solution, the full solution. So you can see that at early times we have an anti-kink here, which follows a kink, and then the anti-kink here is faster. At some point, the two solitons collide, and after that, the kink, which was slower, is now behind the anti-kink, which is faster. And one of the things that we calculated indeed was the trajectories of the two solitons at the early and late times. So here, if you look at, very carefully, you can see that the faster soliton is advanced a little bit during the interaction or during the collision, whereas the slower soliton is retarded. So this is the phase shift that we calculated last time. And this is more easily seen when we look at the contour plot of the energy density. So here, this is the trajectory of the faster soliton, which in this case was anti-kink, and this is the trajectory of the slower soliton, which in this particular case was kink. And as you can see, during the interaction region, they become close to one another. They seem to attract one another. And at late times, the slower soliton, in this case the kink, is behind where it would have been in the absence of the other soliton. So it would have been something like here, whereas it's here. And conversely, the faster soliton, which is the anti-kink, now is ahead of where it would have been in the absence of the other soliton, which would have been somewhere like here. Finally, I showed you an animation of the time evolution. Where you can see the faster soliton, the anti-kink, catching up with the slower kink and overtaking it. I remind you that the reason why we found the kink and an anti-kink in the two soliton solution in an analysis that we did last time was that we chose the sign of the two Backlund parameters A1 and A2 to be positive. And we saw that despite the fact that a single soliton with the positive Backlund parameter is a kink, in fact, when you keep applying the Backlund transform, the nature of the soliton that you add depends on what you had before adding it. And in this case, when we add the second soliton, it becomes an anti-kink. So there are three more cases corresponding to the other possible choices of signs of the two Backlund parameters. And I ask you to look at those cases in the exercises, but let's see a few plots here. So here is a plot of a kink-kink solution, where you see the two Backlund parameters have opposite signs. And you can see clearly that at early times, we have a kink, which follows another kink. And the two kinks here are moving one against the other. So at some point they will interact. And then here you have the kink, which is moving to the left, and the other kink, which is moving to the right. And it's a little hard from this plot here to identify a phase shift. But again, we can look at the contour plot of the energy density where things are now clearer. So here are the two kinks moving against one another. And you see that after the collision, so the solid kink, which is moving to the right, is now advanced. And the kink, which was moving to the left, is now retarded. And another thing that you can observe here is that the two solitons, the two kinks, seem to repel each other. So they get further apart from one another when they interact, and also they seem to swap identities. So what I mean by that is that from this picture, it looks like there are two trajectories, this one and that one. On the other hand, this kink here has the same shape and velocity as this kink here, whereas this other kink has the same shape of velocity as this one. And now let's look at the time evolution. So here you go, you see the two kinks going against one another, and here they repel and they bounce back. Or alternative, you can interpret it as saying that they swap their identity and they keep going with the same shape and velocities. So to summarize, we have the following interpretation of plots of two soliton solutions. So there seems to be an attractive force between kink and anti-kink. And the repulsive force between kink and kink, or anti-kink and anti-kink. So what we observe is that kinks and anti-kinks behave very similarly to particles with electric charge, for instance, the electron and the positron. But the role of electric charge here is played by the topological charge. And so in particular, we see that we have an attractive force when you have opposite topological charge. Whereas we have a repulsive force when we have objects of the same topological charge. Or in fact, more generally, it's the sign of the topological charges of the two objects which matter. So it's quite amazing that lump-off fields can behave so similarly to elementary particles. And in fact, in the 1950s and 1960s, the mathematical physicist Tony Scherm used a higher dimensional version of the kink and anti-kink to model the behavior of protons and neutrons in atomic nuclei. So the original idea didn't quite work in its first incarnation, but it proved over the decades to be a very far-reaching idea, and this is still being studied nowadays. Okay, this is very interesting. Objects of like topological charge repel each other, and objects of opposite topological charge attract each other. So this leads to a natural question. Which is the following. So since kinks and anti-kinks attract, can they stick together or in the parlance of physics, can they form a bound state? Much like, say, the proton and the electron attract one another and they can form a bound state, which is a hydrogen atom. And the answer to this question is yes. And the bound state is the breather that we now move on to study. This takes us to section 5.8, the breather. We start by recalling the general two-soliton solution of the Sine-Gordon equation. Which I remind you takes the following form. U is equal to 4 arctangent of A2 plus A1 over A2 minus A1 times exponential of theta 1 minus exponential of theta 2 over 1 plus exponential of theta 1 plus theta 2. And next we observe that this is a solution for any A1 and A2, even complex values of A1 and A2. On the other hand, the Sine-Gordon field U is an angular variable, and so it should be real. Then there are essentially two options. Option 1 is that the Backlund parameters A1 and A2 and the integration constants C1 and C2 are real. This is what we've considered so far. But there is a second option that A1 and A2 are complex conjugate to one another. And similarly for C2 and C1. So this is what we're going to try next. A comment, to be precise, we can also shift the integration constant C1 and C2 by an integer multiple of pi times I. And this has the effect of permuting the two solitons if the integer is odd, or has no effect if the integer is even. So anyway, since that is just a relabeling, we're not going to consider this next. Let's check now that option 2 indeed leads to a real field U. So I'll start by taking the complex conjugate of U in equation 5.34, which I'll copy and paste now. And I'll just write a complex conjugate. Next, I use the fact that the arctangent as well as the exponential, which appears in the argument, are a complex analytic function, which means that the arctangent of the complex conjugate is the complex conjugate of the arctangent, and the same for the exponential. So we get 4 arctan of A2 bar plus A1 bar over A2 bar minus A1 bar times e to the theta 1 bar minus e to the theta 2 bar over 1 plus e to the theta 1 bar plus theta 2 bar. And next we use the equalities that define option 2. So A2 and A1 are complex conjugate, and same for C2 and C1. And that in particular means that the exponent theta 2 is also the complex conjugate of the exponent theta 1, since the coordinates are real. So we get 4 arctangent of A1 plus A2 over A1 minus A2 times exponential of theta 2 minus exponential of theta 1 over 1 plus exponential of theta 2 plus theta 1. And now we see that this is precisely equal to U, the original field, by canceling a couple of minus signs. Good. Now that we've checked that the field U is real with option 2, let's investigate this solution a little further. And to make our life easier, let's try a solution with general A1, which I will call A, but with C1 and therefore C2 equal to 0 for simplicity. So the integration constants vanish, but the two Backlund parameters are complex conjugate to one another. Next, let's make a few definitions. So first, I remind you A1 was equal to A. So let's call capital A and capital B its real and imaginary parts. And let's call phi its argument. Then A2, which is the complex conjugate of A1, so it's the complex conjugate of A, that's equal to big A minus I big B, which is absolute value of A e to the minus I phi. So here A, B, and phi are real. And then we let theta 1 to be alpha plus I beta, and theta 2 to be alpha minus I beta. So alpha and beta are the real and imaginary part of theta 1. So there are real functions of x and t, because I remind you the exponents theta 1 and theta 2 dependent on x and t. And we'll determine these functions below. Here are the substitutions again. So now let's rewrite the field in terms of these new parameters and functions. So I remind you that the tangent of u over 4 was equal to, we had the A2 plus A1 in the numerator, that's absolute value of A times e to the minus I phi plus e to the I phi. And then in the denominator, we had the A2 minus A1, so absolute value of A, e to the minus I phi minus e to the I phi. And that multiplied e to the theta 1 minus e to the theta 2 in the numerator, so we get e to the alpha times e to the I beta minus e to the minus I beta over 1 plus e to the theta 1 plus theta 2, which is 1 plus e to the 2 alpha. I'll simplify the absolute values of A. And then I'll use trigonometric and hyperbolic functions to simplify. So we get, for the first factor, and the numerator is 2 cos phi, and the denominator is minus 2i sine phi. For the second factor, we get the dependence on alpha is 1 over 2 cos alpha, and the dependence on beta is 2i sine beta. So if I simplify the factors of 2 and 2i, we get minus cotangent of phi times sine of beta over cos of alpha. Good. So to finish, let's determine the real functions alpha and beta in terms of the coordinates x and t, and the parameters, say, absolute value of a and phi. I remind you that alpha and beta were the real and imaginary parts of θ1, which in turn was equal to 1 over a1 times x plus, but a1 is a, minus a1, which is a, times x minus, plus the integration constant c, which were c1, which are setting to 0. So this is the expression in terms of the light cone coordinates x plus and x minus. Next, I'm gonna rewrite this by multiplying by a bar and dividing by a bar in the first term. So I'll get a bar over absolute value squared of a x plus minus a x minus. And finally, let me rewrite everything, or at least what appears in the numerator, in terms of capital A and capital B, the real and imaginary parts of A. So we get A minus IB over absolute value square of A times x plus minus A plus IB times x minus. Therefore, if we look at the real part of equation 5.45, we find that alpha, which is the real part of θ1, is given by capital A over absolute value square of small a times x plus minus capital A times x minus. And it's convenient to factor out capital A over absolute value of A, so that then we have x plus over absolute value of A minus absolute value of A times x minus. And now I hope you recognize that in the brackets, an expression which is very similar to what we had when we obtained the one-soliton solutions of the Sine-Gordon equation by Backlund transform of the vacuum, except that now the Backlund parameter A is complex, so we have absolute values of A instead of A itself. So next, the algebra continues very similarly to what we did when we constructed the one-soliton solutions as Backlund transformed of the vacuum. So I'll let you work out the details. This is the same as after equation 5.15. And eventually we find that alpha is capital A over absolute value of small a times gamma times x minus vt. And since capital A was the real part of small a, which in turn is absolute value of a times e to the I phi, we can write the prefactor as cosine of phi, and that multiplies gamma times x minus vt. Where here we set v, the velocity, to be absolute value of a squared minus 1 over absolute value of a squared plus 1. You'll recognize the same expression that we had earlier for the velocity of one soliton solution, except that now a is complex, and so it's replaced in this expression by its absolute value. And then gamma, the Lorentz factor, which is 1 over root of 1 minus v squared, evaluates to 1 plus absolute value squared of A over 2 absolute value of A. Similarly, you can calculate, and this is exercise 33, beta, which I remind you is the imaginary part of theta 1, and that is equal to B over absolute value of A gamma times Vx minus T, or again, using equation 5.42, B over absolute value of A is nothing but sine of phi, and that multiplies gamma times Vx minus T. Now that we have expressed everything in terms of the original coordinates x and t and the parameters absolute value of A and phi, the phase of A, we can now substitute in expression 5.44 that we wrote earlier to find the following form of the solution. Remember, tangent of u over 4 was given by equation 5.44 to be equal to a prefactor, which was minus cotangent of phi. We'll leave that as it is. And then the dependence on x and t was through a ratio, where in the numerator we had the sine of beta, so that's sine of sine phi times gamma times Vx minus t. And in the denominator, we had the hyperbolic cosine of alpha. So that's cos of cos phi times gamma times x minus Vt. And this is the so-called breather solution of the Sine-Gordon equation. Let's look at this breather solution more closely. So first of all, notice that in the numerator, you have an oscillatory wave modulated by a sine. So this is an oscillatory carrier wave. And on the other hand, everything else, we can view this as an envelope. And the envelope is moving at the group velocity which in this case is equal to v, because the dependence on x and t is through x minus v times t. On the other hand, the oscillatory carrier wave moves at the phase velocity, and that phase velocity is 1 over v, because the dependence on x and t is through vx minus t. So if we factor out v, we have v, which multiplies x minus 1 over v, the phase velocity, times t. And notice that the group velocity v is less than 1, which is the speed of light, and this is as it should be for a solution of a relativistic field equation. To understand why this solution is called the breather, let's set absolute value of A to be equal to 1, which means that the velocity is 0, which we can always achieve if the velocity parameter V is non-zero by switching to a comoving frame. When we do this, the breather solution simplifies to the following expression: tangent of u over 4 is equal to, so we have minus cotangent of phi in front, and in the denominator we had hyperbolic cosine of phi, and then gamma is equal to 1, and x minus vt is equal to x, so we have cosh of cosine phi times x, whereas in the numerator we have sine of sine phi times gamma, which is equal to 1, v times x, which is equal to 0, and then we have minus d. So the minus sign cancels the minus sign in front, and we get the following expression, 5.50. Where we see now that the oscillatory behavior is in time, and in particular the field looks like a bouncing or breathing bound state of a kink and an anti-kink, as will become clearer shortly as soon as we look at pictures. And this bound state is periodic in time, so it has some time period tau, which is equal to 2 pi over absolute value of sine phi. I write the absolute value to make sure that the time period is positive. This is the periodicity that we observe by looking at the numerator in 5.50. The solution is also localized in space because this hyperbolic cosine in the denominator is such that u goes to 0 exponentially fast when x becomes large and positive or large and negative. Here's a plot of a v equals 0 breather solution. I took phi to be pi over 10. So here you see x and t, time, and the field u is plotted vertically. So first notice that I have drawn one time period here. And if we fix time, say between minus tau over 2 and 0, so we're somewhere here, you see that the field u initially starts at 0, then it goes down, so this would be an anti-kink, and then it goes up. This is a kink, so it's back to 0. So when time t is between minus tau over 2 and 0, we have an anti-kink on the left and a kink on the right. And then when time is equal to 0, the positions of the kink and the anti-kink are swapped. And so we see that here afterwards, first u increases, so we have a kink on the left, and then it decreases, we have an anti-kink on the right. And if we extended the solution further in times, you will see that this bounce continues. It's useful to look, as usual, at the contour plot of the energy density. So here it is. where you can indeed see the trajectory of an anti-kink here and the trajectory of the kink there. So what happens is that the kink and the anti-kink attract each other, and so they cannot get infinitely far from one another, but at some point attraction brings them together until here they swap their positions. And again, this is a plot of a single time period. So what would happen is that the anti-kink does something like this, and then again, it goes back to the left and then to the right, left, right, etc. And the kink does the mirror image of that. Finally, let's look at the time evolution, which I think makes it even clearer why the solution was called a breather. Here it is. So you see an anti-kink on the left, a kink on the right, and now we have a kink on the left, anti-kink on the right. And as time goes by, this continues periodically, breathing slowly up and down. So here I consider phi to be equal to pi over 10, but I have a few more pictures that you can find on Duo for different values of the parameter phi. So for instance, here is phi very close to 0, more about which in a minute. Here is phi equal to pi over 4, and here's phi very close to pi over 2. So both the limits where phi is very close to 0 or it's very close to pi over 2 are interesting to consider, but let me just make a couple of comments on the phi to 0 limit, and then we'll wrap up for today. So my comment is that as phi tends to 0, the time period of the breather which was 2 pi over sine phi, this will go like 2 pi over absolute value of phi, which tends to infinity. So the time period diverges, and it's also possible to see that the special size of the breather let me call that x max, goes like, and that's exercise 34 in the problem sheet. The special size of the breather goes like the logarithm of 1 over absolute value of phi, so it also diverges, but it diverges logarithmically rather than with an inverse power law. So what's happening in this limit is that the kink and the anti-kink are more and more loosely bound. So in the strict limit, they're no longer bound, and they just go through essentially half of their oscillation, where, say, the anti-kink, which started on the left at minus infinity, ends up on the right at plus infinity, and vice versa for the kink. And their separation grows logarithmically. As a final comment, and you can read a bit more about this in the lecture notes, one can define so-called binding energy of the kink and the anti-kink inside the breather. So that's defined as the energy of the breather minus the sum of the energy of the kink and the anti-kink in isolation. And we can calculate the energy of a V equals 0 breather by plugging the solution that we just found into the general formula for the energy density of a sine-Gordon field and calculating the integral. And when you do that, you should find that that's equal to 16 cosine of phi. And then we have to subtract the energy of a kink, which was 8, as we calculated in the chapter on the Bogomolny bound, and similarly for the anti-kink. So we see that the binding energy is minus 16 times 1 minus cosine of phi, and so it's negative, meaning that it lowers the energy of the state. And so when phi goes to 0, the cosine goes to 1, and the binding energy goes to 0, which means indeed that the kink and the anti-kink are no longer bound together. That's all for chapter 4 on the Backlund transform. In the last 3 lectures of the term, we'll look at chapter 6, which is about the Hirota method, which is a method that allows us to construct multi-soliton solutions, but now of the KdV equation. See you next time.